So one of these important conceptual things is that the electric field lines concept. So this concept basically tells you that if you have like many charges and the electric fields is produced, these electric field lines, right? Field lines start at positive charges and end at negative charges. Okay. So in that case, because of that reason, the positive charges are usually called the source of field lines. And negative charges are called the sink of field lines. Right? I mean, in any case, the field lines basically start from the positive charges and end up in negative charges. So anywhere else, they don't do anything, right? So the electric field lines are somewhat continuous, okay? I mean, there might be some perhaps exceptions to this rule, but I mean, usually it's like that. So if you just look at these kind of pictures, this picture actually is quite similar to a flow picture, like a water flow, for example. If you have some kind of a source of water in here, let's say, I don't know, a faucet, for example, water is produced in here, or I don't know, this is in the ground and the water is kind of coming out from the ground and then it's just coming out like that. And there is a sink in here, sink. And so as a result, you would actually see that the water is kind of flowing like that. So it's everywhere, but the flow of the water somehow satisfies more or less the same thing. So in any case, there's this kind of an analogy between the electric field lines and the flow lines of water, for example. And some people may take this analogy seriously. So let me just make this warning here. We're not claiming that the electric field is something like this, right? I mean, in the electric field, there's something flowing, right? We don't claim that. That's not true. What we are claiming is that the mathematics that governs the behavior of the electric field lines is essentially the same as the mathematics of the flow line, the water flow lines, right? So they have the same mathematics, but different physics, obviously. Okay. So again, just keep in mind that there's nothing flowing. But we have this idea here of conservation of water, for example, right? I mean, if you just think about some kind of a surface in here, just think about this kind of a surface in here. Just think about these flow lines. If this is a water flow, for example, that cross that surface, right? So I can use this surface to express the amount of the volume of water that crosses the surface per unit time. And there's actually some kind of conservation of matter in here. So, I mean, from the surface, for example, every flow line that crosses the surface is also going to cross that surface. So as a result, the volume per unit time that crosses this surface should be equal to the same quantity in here, right? That's the conservation of matter, basically. Whatever water is crossing in here, it should be the same amount of water that should cross the second surface, okay? So the same property holds also for electric fields, right? So as a result, at first we make an analogy to flow, but then, of course, we forget about the analogy and then we just use this as some kind of a mathematical relationship, okay? So to express this idea, we are going to define what we call as a flux. So flux is basically a word that essentially means flow or something like that, right? Probably it's a Latin word. Just think about the water flowing inside a pipe, for example, with velocity v. Let's just take a section in here of that pipe, for example. This is a surface. In the previous semester, we have defined the area of such kind of a surface as a vector which is perpendicular to the surface itself, right? And the velocity vector in here is going to be like that. So the flux in here is essentially the dot product of the velocity with the area. Okay. So this thing has the advantage of, like, I don't know, I mean, if I choose a second surface in here like that, perhaps, in which case this is going to have a different area vector. So let me call this as A prime. So in that case, the conservation of matter actually tells you that this quantity is the same for that surface as well. So it basically expresses the fact that every water molecule that crosses this surface also crosses that surface as well, right? So there's a dot product in here that's somewhat involved. So when we are defining the electric flux, we are going to do the same thing essentially, but instead of velocity, we are going to define the electric field, right? So the basic idea is this. So first we define this for a surface, a general surface. So that's a surface. I'm going to talk about this, what I call as geometric area. All right. I'm going to call this as A, right? So that's a scalar thing. We are going to define a quantity that's called the surface normal. N, right? That's surface normal. So that's a unit vector perpendicular to the surface. So for a surface, the surface normal essentially gives us an idea about the orientation of the surface, right? So we describe the orientation of a two-dimensional surface by specifying the vector which is perpendicular to it, right? So that unit vector is perpendicular to everything on the surface. So let's just show it like that. Okay? So there are actually two possible surface normals. So if n is a surface normal and minus n is also a surface normal. Is also a surface normal. It's just that it's a different direction. And in these cases, there's always a choice involved in here. So in any case, the area vector, or simply area, that we call is basically a vector whose magnitude is equal to this geometric area and whose direction is the surface normal. Okay. So in any case, I'm going to describe the area of a surface as a vector which is perpendicular to that surface. It's parallel to the normal. Just like the choice of the normal involves some kind of a direction of choice for the normal, the area is also, I mean, there are two possible ways that I can express the area vector, depending on how I choose the surface normal, right? Just keep this in mind. So there's some kind of arbitrariness in that. Okay. If I have a surface in here with area A, area vector A, and if I have an electric field in here, so I'm going to show the electric field like that. So these field lines are basically crossing that surface, right? So the field lines are entering to the surface. Sorry, it is crossing the surface from one side and to the other side, right? You just cut the surface and then pass to the other side, okay? In any case, so if you just think of this as some kind of a water analogy, this means that the water is crossing the surface and passing from one side to the other one, okay? So in that case, let's call that angle as theta. The electric flux, we are using this capital phi symbol for that, is given as the dot product of the electric field with the area. So as a result, in terms of this angle, is basically the product of these two multiplied with the cosine of the angle between them. Okay, so in the case of water flow, this has a clear meaning. So that flux is basically the volume transferred per unit time or something like that. Okay? No, it's volume transferred per unit time. For the case of electric flux, we don't give any physical meaning to it, right? It's just a mathematical quantity, but in a moment, we are going to say something about this, this flux. Yeah. So there are a few things that I should mention in here. For example, in here, basically the flux is positive. Positive means that the electric field lines cross the surface in a way which is parallel to the direction of the surface normal. Okay, there are these situations in here where, I mean, let's just describe these two situations. Surface area is like that, but the electric field is parallel to the surface. Okay. In that case, flux is equal to the dot product, obviously. So it's the product of the electric field area and the cosine of the angle between them, which is 0. Okay. In that case, the field lines are parallel to the surface and they don't cross it, right? In the water flow analogy, water is just flowing parallel to the surface and it doesn't pass to the other side. And so therefore the flux is equal to 0. And then we have this other extreme situation. It's not the extreme, sorry. The other situation. The area is like that. But the electric field lines cross the surface like that. Right? So it is, the electric field is like that. Right? So they intersect the surface at that point, then from this side, they pass to the other side, right? From this side, they pass to this side. Okay. So as a result, field lines cross the surface opposite to the direction of the surface normal. And so in that case, the flux is negative in that case. So theta is an angle which is bigger than 90 degrees. So therefore, this is negative. Okay. So in a way, phi is the, sorry, I'm not going to write this thing down because I don't know what to write that thing down. But think of that, I mean, this is actually quite meaningful in the case of water flow. So how much water flows along the direction of this arrow, along the direction of the surface normal? It can be positive, 0, or negative. Negative means that the flow is in the other direction, right? In that case, you can then think of the surface normal as some kind of a direction of some axis or something like that. Okay? Just keep this in mind. Okay, so the idea in here is this, in this kind of a picture, if I draw several electric field lines like that, right? Sorry about that. And if I consider some kind of a surface in here, I don't know, let's say that this surface has some kind of an area, A1, let's say, and consider another surface in here. It's going to have a bigger area in here, so let's just call this as A2. So in here, for example, there will be some kind of electric field lines in here. Let's just call them E1, and the electric field is going to have I don't know, a different magnitude in here. Let's call this as E2. In any case, so we can basically compute the flux that's crossing that surface in here and the flux crossing that other surface. So the idea in here is that these two fluxes are the same, right? So if every electric field line that crosses this surface also crosses that other surface, then these two fluxes are the same. I cannot show it in here, but I'm just going to give you a general discussion in here. And so the first thing that you need to understand about Gauss law is this. So we're kind of talking about the equality of the fluxes. Okay. All right. I mean, that's the idea essentially. But now I would like to express this Gauss law in terms of closed surfaces. Right? Closed surface means there's also an open surface. Open surfaces like a square, for example. Like this is a square. It's actually a surface that doesn't enclose anything. It has a boundary, for example. Right? This square, for example, these 4 edges, right? This is the boundary. A closed surface is like a cube, for example. Cube. It encloses some space. So there's something called a region which is inside, and there's also some region which is called outside, right? So I'll be basically talking about this kind of a thing. So another example is the sphere, for example. It's hard to draw a sphere in here. It basically looks like a circle, but think of this as a two-dimensional spherical surface. So there's this analog in here as an open surface, for example. Disk is an open surface, for example. I can compute the electric flux through these kind of open surfaces as well. No problem with this, but the Gauss law is basically expressed in for closed surfaces, right? So the idea is something like that. So suppose I have a point charge in here. Let's say single point charge outside. Okay. So I have a point charge. Let's say this is a positive charge, right? And I have something in here. I'm going to show all the Gaussian surfaces, closed surfaces like that. So that's a closed surface. Okay. So the idea in here is this. Every electric field line that starts from this positive charge either doesn't cross the surface in here, or if it crosses, there's a point where it enters into the inside, and there's a point where it exits, right? So it enters somewhere, it exits somewhere. Okay. Sorry, I made a mistake in here in discussing the surface normal. I should actually say that there's something. I should talk about the surface normal in here. Sorry about this. Let me go back to this. So for closed surfaces, we just define the surface normal to be pointing outside. So that's a convention. So let's add this convention. Define surface normals pointing outward. Okay. So as a result, for the cube, for example, the surface normals would be like that on that surface. But it would be like that on this surface, and like that in that part of the surface, and so on, right? And for the sphere, of course, every place, everywhere on the surface, we have a different direction. So in those cases, if you have like a sphere, for example, what you need to do is to first of all choose as some small area element in here. I'm going to call this as dA. dA is called the area element. It's an infinitesimal area element. There's an infinitesimal, there's a surface normal in here, n hat, all right, perpendicular to the surface. So we just define the area element as a vector as this area multiplied with the surface normal in the same way. In that case, flux through that closed surface is defined as the integral of the electric field dotted with this thing here. So basically what we need to do is compute the flux through all of these infinitesimal surfaces and integrate it. To express the fact that this integral is over a closed surface, we put an O sign in here. So an integral with an O sign means that the integral is actually over a closed surface. Just keep this in mind. It's just a notation, right? I mean, we have nothing to do with this. So in any case, so the idea in here is this: when the electric field line exits a closed surface, the flux is positive in that. So at these regions, the electric field lines move from inside to outside. So therefore, they move parallel to the surface normal. So the flux would be positive in here. When the electric field lines enter at these points, for example, in that case, the flux would be negative. Okay. So that means when you have a single point charge outside, the electric field lines produced by that point charge is going to enter inside from that surface and then exit. And so as a result, they are going to produce a negative flux in there and a positive flux. And it turns out that if you sum them up, they both end up to be equal to zero. So the electric flux of the electric field produced by that point charge is going to be equal to zero for any kind of a closed surface. provided that the charge is outside. Okay, this fact expresses the fact that field lines enter and exit the surface. Right? They enter inside and then exit. And so therefore the flux is first negative and then positive, but when you add them up, you get zero. Okay. But on the other hand, if you have a single point charge inside, point charge inside, we have a situation like that. I'm going to do it like this. So that's the my Gaussian surface. I have a point charge inside. In that case, all the field lines that actually start from the charge, they actually cross the surface and go out. There's no entering. I mean, if the surface is kind of complicated, there might it might also first exit, then enter, and then exit again. Or these kind of complicated things happen. But at least for a simple surface like that, you can see that all the fluxes are positive now because all the electric field lines are exiting. Right? So all the fluxes are positive. Okay. In this situation, the electric field lines, the electric flux through that closed surface would be positive. Okay. Now, it turns out that this electric flux is also proportional to the charge, and it doesn't depend on where the charge is. And the result is basically Q divided by epsilon. Okay. So that means, like, if you just compute the electric flux of a point charge crossing a closed surface, that total flux is zero if the point charge is outside, and that flux is equal to Q divided by epsilon zero if the charge is inside. Okay. If the charge is positive, this is positive. If this was a negative charge, then the flux would be negative, but since the charge is also negative, this is kind of consistent. So I think I should have said flux is positive everywhere in here. Okay. So that's the idea, right? And so as a result, we then express the Gauss law like that. So the Gauss law essentially generalizes this for any kind of a charge distribution. Okay, it says that for any closed surface, the flux integral over the surface of that Gaussian surface is equal to the enclosed charge divided by epsilon zero, where Q enclosed is the total charge inside. Okay. So that's the expression in here, inside. Sorry, I have some problems with angles. Right? That's our Gauss law. I mean, I'm just going to show one simple example in here. So if I have like, I don't know, 3 point charges, let's say, I don't know, Q1 in here and Q2 in here and Q3 in here. In that case, the electric flux integral is going to be equal to Q1 plus Q2 divided by epsilon zero. So therefore, I'm going to write down only the charges inside. Where they are inside the surface is not important. Any outside charges, they are also not important as well. They don't contribute anything to the flux. So as a result, we have this kind of equation. Right? This doesn't mean that the outside charge doesn't produce an electric field in here. It doesn't mean that. So the outside charge also produces an electric field in this region, but somehow the total flux due to that electric field is equal to zero. Right? I mean, you can actually kind of think of it like this. This is 0 times Q3. So somehow this electric field depends on Q3, but its integral is equal to 0. Okay, and try to think of it like this. Okay, so the first thing that we need to say is that this Gauss law is the same thing as Coulomb's law. Sorry, it's not the same thing. It's basically an alternative way of expressing the Coulomb's law. If you remember, the Coulomb's law says that the electric field produced by a point charge is 1 over 4 pi epsilon 0 Q divided by R squared. So therefore, this is a different mathematical expression actually, but it essentially expresses the same thing. So this means that starting from the Coulomb's law, you can deduce the Gauss law, or starting from the Gauss law, you can deduce Coulomb's law, right? So they are mathematically equivalent to each other, but they are different ways of expressing the relationship between the electric field and the charges that produce that electric field. So in the Coulomb's law, we just have to express the electric field as an integral of charge. Here, or for the Gauss law, we have an integral of the electric field is expressed in terms of the charges, right? So different mathematical expression, but the content is the same. Okay. So why do we learn this? Basically, Gauss law is actually a nice method to solve some electric field problems. So if we have a continuous distribution of some charges, let's say, you would like to compute the electric field produced by these charges. This is usually a very difficult problem. In some problems, I can use Gauss law to solve the problem quickly and easily without any hassle if the problem has sufficiently high symmetry. There are some problems where I can solve the electric field easily and by using Coulomb's law, for example, right? There are places where Coulomb's law is easier. There are some places where the Gauss law is easier. Just keep this in mind. So there are some certain kinds of problems where which are quite difficult by Coulomb's law, but it's very easy by using Gauss law. Okay, so as a result, I mean, we are going to think of this Gauss law as a mathematical technique for solving some electric field problems. Basically, let's say it like this. If problems have one of the following symmetries, right? So the first one is called the spherical symmetry. I mean, a charge distribution is spherically symmetric, for example. Point charge is included in here. A uniform charge sphere is included. A spherical shell is included, and so on. Right? There are lots of examples in here. Infinitely many number of examples. Second type of problems are the problems with cylindrical symmetry. And then the third number of problems are like the planar symmetry. Cylindrical symmetry means it's the symmetry of an infinite cylinder. So again, infinite line is a type of a problem in here. An infinite cylinder, infinite cylindrical shell, and things like that. Right? For the planar problem, we have the infinite plane and infinite slab and things like that. Right? There are also some number of problems that we can solve in here. Right? So I'm going to solve a problem in each kind, but I'm just going to just solve this point charge problem in here. And infinite line of charge problem for this one. So it's like a thin line of charge. And then we are going to solve the thin sheet problem from this kind, right? So I'm going to actually solve from each one. However, okay, the description of the symmetry and the use of the mathematical methods and some details in there, I mean, these have to be explained clearly, and I don't have time to do that in here, so I cannot repeat all the steps in here because these are quite complicated. So I think through some sample problems, I have explained all of them. So probably I have started with the point charge thing. All right. So first I described the spherical symmetry and then what that symmetry implies in terms of the electric field and things like that. Right. So here, like in 20 minutes, I'm just going to solve these three problems in here, but without much explanation in a way, without going into the details. But I'll try to explain. Right? So I'm going to start with this thing in here. So the first problem is this one, right? Find the E field produced by a point charge Q at a point at distance r from the charge. Okay, so basically I have a charge in here plus Q charge. It's a point charge. I have a point somewhere in here where that distance is r, and I would like to compute the electric field in there. So that's simple, obviously. This is Coulomb's law, right? So we are going to get the Coulomb's law, but we are going to do this by using Gauss law. So in a way, we are going to show that the Gauss law implies the Coulomb's law, right? So that's actually one part of the equivalence. So as a result, we are going to see that, I mean, we can actually solve the problem easily by using that point of view as well. It is kind of pointless for a point charge, but if you have a sphere, for example, uniformly charged sphere or a spherical shell or whatever, in that case, well, this is actually much more easier than the chapter 21's method of integrating the Coulomb's law expression. Okay, so the idea in here is this. I have a point charge in here, and then I have a point at a distance r from that point. So let me use something like that. Right? So there's an electric field in here, right? I'm going to write the electric field in here. Okay, so let's just remember the radial unit vector in here. So we have earlier said that the electric field in here can be written as the radial component of the electric field multiplied with the radial unit vector. So E in here is called the radial component of the electric field. Okay, so R is the radial unit vector. Right. In a way, you can kind of think that this E is the magnitude of the electric field, but it's not really magnitude. This can be positive or negative. So if this charge is positive, that E is positive. If charge is negative, then this E is negative, okay? So as a result, because of that reason, I would like to call this as the radial component. So it can be negative too. We don't have any problem with negative charges, okay? But when I'm drawing, I will usually draw this vector pointing in the outward direction. In any case, what we are claiming is that that's basically the implication of the symmetry. So if you just consider any point with a distance r from the center, the electric field has a different direction. So therefore, it's a different electric field. But let's say it like this. It is the same radial component. So let me do this too. All right. So I'm going to say that this radial component is going to be the same radial component. Okay. So I can basically do this for all the other points. So as a result, I imagine some kind of a surface in here. This is essentially a sphere. I think I should have drawn this with a different color. But let me do this actually, right? I'm going to use a green color now. So if you think about the sphere with a radius r. So unfortunately, I have to draw the sphere as a circle in the shape of a circle. In any case, everywhere on that sphere, basically the electric field has the same magnitude, right? Same direction. Well, it's the radial outward direction, so therefore the directions are different, depends on the point. But in any case, so the idea therefore is to choose this as our Gaussian surface. Why? Because I don't know the magnitude of this electric field, but at least at every point, the electric field has the same magnitude. So therefore, I have like a single unknown. I can express the flux in terms of a single unknown. Okay. So in any case, there is also a surface normal at every point. This surface normal, in that case, is equal to the radial unit vector. So the surface normal also coincides with that direction of the electric field. Okay. So in any case, if I just choose any surface element in here and express the flux in here, sorry about that. So first, let's write down the Gauss law. So over that surface, the electric flux is equal to the enclosed charge divided by epsilon zero. So the right-hand side is the easiest to compute. It's just the total charge inside divided by epsilon zero. The charge is at the center, so yeah, whatever. It is Q basically. So that part is easiest to compute. Okay. This part is a little bit difficult. Right? So first thing that we know is that this electric field is equal to E times R. The area element is equal to the area multiplied with the surface normal. So as a result, in here, we have the product of these two scalar quantities, E times dA, and the dot product of the radial unit vector and the surface normal. But this time, this is equal to 1. Okay, so therefore, this integral can be expressed as the product of the radial component of the electric field with the area element. Right? So that's the first step. So that's step 1. We convert the dot product of two vectors to a product of their radial components, okay? In the second step, we just notice that this is constant. Notice that the electric field is not constant. It's the radial component of the electric field, which is constant, okay? So in calculus, we know that if something is constant, I can take it out of the integral. So that's what we do. So take the electric field, radial component of the electric field outside. And then inside, we have an integral of area. Right? So that's the second step. So that's step 2. And then we have step 3. In step 3, we just realize that this is basically geometrically total area of the Gaussian surface. So the area of the Gaussian surface. Gaussian surface is basically an imagined closed surface in which we evaluate this flux integral, right? So in this case, this is a sphere with radius r, so therefore its total surface area is 4 pi r squared. On the right-hand side, we have q divided by epsilon zero. So therefore, from here, we just deduce that the electric field is equal to 1 over 4 pi epsilon zero, q divided by r squared. Okay. As I said, I mean, instead of a point charge, if I had a, I don't know, a sphere in here, for example, I would have found the same result too. Whatever the, I mean, as long as the charge is distributed uniformly over the sphere, in a spherical symmetric fashion, perhaps, the derivation is going to be the same. So since the right-hand side does not depend on how the charge is distributed, the same result is valid for these kind of cases as well. Okay, but as a separate problem, I'm not going to solve it in here because writing the problem, describing it, and writing solution, this takes time. But you can solve it very quickly, right? So in any case, so the second thing is that, yeah, we started with the Gauss law and deduced the Coulomb's law. I said that you can start from Coulomb's law and go back and you can also deduce the Gauss law. I tried to give some kind of an idea of how this is done, but yeah, I mean, there are some certain mathematical details in there. Okay. So, all right. Next, this problem, right? This is infinite line of charge. Okay. So in that case, some charge is uniformly distributed to an infinite line. So physically, I would say that this is a very thin line where the thickness is negligible. But mathematically, we just think of this as a line with zero thickness, and it is infinite in length. So therefore, there's a total of infinite charge. So to describe the distribution of the charge, we use the linear charge density. So lambda in here is the linear charge density. So that's equal to basically charge divided by length, right? Since the total length is infinite, the charge is infinite too. So to compute this, we just choose some kind of a finite portion of that line, and then the amount of the charge in here is going to be proportional to the length in there. And the proportionality constant is the linear charge density. In any case, there's the problem in here is this, we just choose a point somewhere in here, and let's say that r is the distance to the axis. So r is slightly different in here. It's not distance to a point, distance to an origin. It is distance to an axis, right? Just keep this in mind. And we would like to compute the electric field. Okay, so quick solution. So in that case, the Gaussian surface, so I'm going to do it like that, right? So that's the infinite line of charge. We choose the Gaussian surface as a cylinder. So this is a problem with cylindrical symmetry, actually. So an infinite cylinder also satisfies the same symmetry conditions, right? So the Gaussian surface in that case surface is basically a cylinder with radius r. Okay. So the radius of the cylinder, that distance is r. Let me write it down now. Why do we do this? Because we would like to find the electric field at the surface of the cylinder. We would like to find this, right? So when we evaluate the flux integral, that electric field is going to enter into the equations. That's the reason. Now, there's some kind of a symmetry argument in here too. I can basically, I mean, it is quite hard for me to draw these directions of the electric field, right? But you can see that this electric field is basically perpendicular to that psi surface. So in that respect, it is basically parallel to the surface normal. On this cap, however, on that base of the left base of the cylinder, the electric field lines are parallel to the surface. So therefore, there cannot be any flow in here. So the electric field lines are like that. But the surface normal is perpendicular to it. Okay. And on the right side, again, the same kind of situation. The electric field lines are parallel to the surface, but the surface normal is in here is perpendicular to it. So as a result, no flux coming from here. No flux. Again, no flux coming from this base. So there's going to be some flux coming from this side surface, right? I usually do it like that. So I just call this like this left base as 1, right base as 2. So that's the surface 2. And the side surface is 3, right? In any case, let's see. I should have actually said something more in here. This is a cylinder with radius r and length L. So there's some kind of a length factor involved in here. So there's a length of the cylinder as well. Okay, so that's something that's important. Just keep this in mind. Okay, so I'm just going to do some kind of an exaggeration here. So in that case, the enclosed charge is basically the charge that lies inside the cylinder. So I think I'm going to use a different thing like that. So, all right, so I'm going to start from here and then think about that portion of the this line in here, right? It is that portion. So that's actually too much. So make this a little bit smaller, right? So this red charge is the one that's enclosed, right? So that's the enclosed charge. So in any case, we first of all write down the Gauss law. Q enclosed divided by epsilon 0. Let's just compute the enclosed charge first. So since this red part of the line has length L, the total charge on it is equal to lambda L. So that's easier to compute. For the electric flux, I first of all divide this integral into these three parts. So the integral over the first part, this base in here, integral in here, plus integral over the second base, and integral over the side surface. Okay. So the dot product on the first base of the electric field and the surface normal is equal to 0, and similarly for the second one. So as a result, this flux is equal to 0, that flux is equal to 0. But I mean, we can actually tell this geometrically too, since the electric field lines are parallel to the surface. The field lines are not crossing the surface, so therefore the flux is 0. So the only flux is coming from the side surface. All right, so therefore we have just the third integral in here, integral over the side surface. Notice that this O sign disappeared in here. I'm not using any O sign here. Here, the first thing that we need to do is to express this in terms of the, in terms of the surface normals. It's the same kind of a thing. So the first step, I basically convert this dot product into the product of the radial component of the electric field with the scalar area. So the second step, I take the electric field out because the electric field has the same radial component at all points on the side surface of the cylinder. So that's basically one of the symmetry requirements. And the third step is that, this is basically the total area of the side surface. So let me write total area of the side surface. It's not the total area of the Gaussian surface because we don't include the bases. So therefore, this is equal to E times 2 pi r is the circumference of the circle and L is the length, right? So this is the side surface. 2 pi r is the circumference in here. I multiply with the length of the cylinder, and this is going to give me the total area of that side surface, right? Okay. And so on the right-hand side, we have lambda L divided by epsilon 0. So it is the first thing that we had computed. L's disappear in here because it's just a variable that I invented. So therefore, the result is that the electric field is equal to 1 over 2 pi epsilon 0, lambda divided by r. Right? If there are anything that you miss in this derivation, please go ahead and, just review this. Try to understand this actually, because this is one of the fundamental integrals. Right? Sometimes I'm going to ask a question like find the electric field produced by a line, and I'm kind of expecting you to do this at least mentally and then to be able to write down this equation. Okay. So just keep in mind that this 2 pi r geometrical factor, which also appears in here, is the geometrical factor that basically corresponds to the circumference of the Gaussian surface of the cylinder. Now, just keep this in mind. All right, let's just do this quickly for the infinite plane. Can I do this? Yeah, let's just quickly do this. Infinite thin plane. Okay. In that case, the picture is something like that. So that's an infinite plane, but it is infinity in all directions, right? I cannot draw an infinite plane on a picture like that, so I have to draw some kind of a rectangle or something like that and place some kind of things like this. In any case, we are going to use sigma to denote the surface charge density. It is basically charge divided by the surface area. It's the same kind of comment in here. The total charge is infinity because the area is infinite. But if you just take a piece of the surface and then, the charge on that piece of the surface is going to be proportional to the area of that piece. So the ratio is basically the charge density. Okay? In any case, I'm going to basically draw this plane like this from the side view. In that side view, one of the directions of the plane is basically coming towards us. Okay. I usually draw the pictures like that. So let's say that that's the x direction. So if that's the x-axis, that's the y-axis, and that's the z-axis. So basically, the plane is on the xy plane. So on that picture, for example, let's see, y-axis is pointing into the screen, x-axis is towards right, and the z-axis is perpendicular, right? You can also think of it like that, and I'm going to show this sheet like this. Okay, so the problem in here is like this. I have a point in here. Sorry, I'm going to draw it like that. Okay. So this is the infinite sheet. I have a point in here, which is at a distance z from the plane, and I would like to find the electric field in here. Okay. Here, how we choose the Gaussian surface? We choose it like that, right? First of all, this is a cylinder, so I'll try to draw it like that, where the height is basically 2z, and this cylinder somehow divides the picture into two or something. Sorry, the charge plane, the sheet divides the cylinder into two equal parts. As a result, I'm going to consider a cylinder where the height above the sheet is z, height below the sheet is also equal to z. So 2z is the height, right? Why do I do this? Because by symmetry, I know that electric field at every part on this base is equal to E. And the electric field at every point on the lower base is also equal to E, but it's in the opposite direction because there's some kind of a symmetry in reflection symmetry, basically, across the XY plane, right? In any case, I'm going to call the area of the base A. Area of the base. Okay. And for that case, the enclosed charge is essentially the charge that actually is inside the Gaussian surface. So this also has the same area. Okay. So as a result, when we write down the Gauss law, E dot dA, Q enclosed divided by epsilon 0. Enclosed charge is easy to find. The surface charge density multiplied with this area of the charge. This can be also computed easily. So I'm just going to do it like that. So I can divide this integral into these three parts. So I can do this as an integral over the top base, bottom base, and then side surface, right? Since this is a cylinder, I can do it like that. But this time, the flux through the side surface is equal to 0 because the electric field lines are parallel to that side surface in that case, in this problem, in the symmetry type, right? So let me erase all of these. So we have contributions coming from the top base and the bottom base. In each case, the electric flux is equal to the electric field multiplied with the area with the same side. Okay. So the electric field in the bottom base is in the opposite direction. Sorry, is in the opposite direction. But the surface normal is also in the opposite direction too. So the surface normal vector is pointing down, and here it's pointing up. Since both vectors change sign, they have equal contribution. Okay. So therefore, this means that the electric flux is equal to 2E times A. On the right-hand side, we have sigma A divided by epsilon 0. This then tells us that the electric field is equal to sigma over 2 epsilon 0. What's important in here is that this is independent of the distance c. Okay, so you can check the dimensions actually. Dimensionally, it's correct, but the fact that it's independent of the distance c will become useful later when we discuss parallel plate capacitors and things like that. So that's going to be important later. But I mean, try to understand this. Okay, so let me finish here.